Hi, thanks for watching. In this short series of videos, I'm going to take you on an astro safari to some of the strangest and frankly most terrifying objects in the universe and explain what happens to stars, including the Sun, when they reach the end of their lives. Everybody's heard of black holes, but they're only one of the ways that stars can die. There are other end states that are just as exotic. In this video, I'm going to talk about white dwarfs, which is going to be the eventual fate of our own star. But first, let's cover a concept that's central to everything that I'm going to discuss, that of the balance of forces. One side of the balance is always occupied by gravity, which pulls everything together towards the centre of mass. That's very important, remember that bit. If there was nothing to balance against that and gravity could act unchecked, then every object, stars, planets, and even you, would collapse into a black hole. But here's the thing, gravity is actually a very weak force. For all that I'm going to be talking about objects with intensely strong gravitational fields, to demonstrate how weak gravity can be, consider that when you pick up a paperclip with a small magnet, that magnet is outpulling the gravity of an entire planet. So there are various forces that act to counter the inward pull of gravity, and as long as they're strong enough, then any given object is stable. However, if a given force is not strong enough, then gravity will win against it and will crush the object until some other force proves strong enough to resist and provide a new balance. For objects such as people or planets, the counterforce is electromagnetic. The negatively charged electrons surrounding atomic nuclei repel each other, preventing them from getting too close. In a star, it's somewhat different. Stars are made of gas, and as gravity compresses the gas, it heats it up until eventually the temperature and density in the middle of the star reaches a point where hydrogen nuclei undergo nuclear fusion, combining to form helium and releasing energy in the form of radiation. That radiation exerts an outwards pressure, trying to blow the star apart. If the radiation is stronger than gravity, then the star expands, but then the radiation pressure is reduced as a result, and gravity gets the upper hand and compresses it. The two forces reach an equilibrium, and the star settles down and becomes stable, what we call a main sequence star. Stars remain on the main sequence as long as there is hydrogen to keep fusing, maintaining the radiation pressure that keeps gravity at bay. But eventually, the hydrogen in the core of the star becomes depleted, and the radiation pressure is reduced, so gravity begins to win, crushing the core of the star inwards. That heats the core up even further, and if there is enough mass for the crushing to reach a critical temperature, then the helium, that was the ash left over from the hydrogen burning phase, will itself fuse, creating heavier elements such as carbon, nitrogen and oxygen, and providing radiation pressure to once again allow the star to reach a new equilibrium. But a side effect of those higher temperatures is that the outer regions of the star, away from the fusion occurring in the core, will be heated up and expand, puffing up like some sort of stellar popcorn. The radius of the star balloons dramatically, and the star has now become a red giant. This will happen to the Sun. It's about halfway through its lifespan at the moment. In 5 billion years' time, it will expand into a red giant, consuming at the very least Mercury and Venus, and very probably the Earth as well. I don't plan on losing any sleep about it. The Sun will put on a pretty good show for anybody that does happen to be around at that time, because it will form what's called a planetary nebula. So called because in the early days of telescope astronomy, people would see these little ring-shaped or disc-shaped objects and get a little bit excited and think it's a planet. But no, it's the outer layers of the red giant puffed completely off into space, escaping the star's gravity, and then getting pushed away by the radiation of the dying star in the centre and getting lit up to create these quite beautiful objects. So what happens to the remnant in the middle after all of its fuel is exhausted? Well, we finally come to the white dwarf. But before I explain what it is, let's have a little look at how they were discovered. The first to be seen was 40 Eridani b, a very faint companion star to the more sun-like 40 Eridani a, which for Star Trek fans is the home star of the planet Vulcan, but we won't get into that. 40 Eridani b was discovered in 1783 by William Herschel, also famous for discovering Uranus, a real planet, not a planetary nebula. It was thought to just be a very faint ordinary star, as the concept of white dwarfs didn't exist for over another century. The second to be discovered initially made its presence known by its absence. Friedrich Bessel, a great astronomer of the 19th century and the first person to accurately measure the distance to another star, made observations in 1844 of Sirius, the brightest star in the night sky, and he discovered that it had a wobble, that it must be accompanied by an invisible companion. It wasn't until 18 years later that this very faint companion star, Sirius B, was first seen. By the early years of the 20th century, it had become apparent there was something very unusual about these stars. They were white in colour, indicating quite a high surface temperature, and yet they were very faint, indicating they were quite small in size. Astronomers were able to use measurements of those two quantities to get an estimate of their radius, and they seemed to be about as big as the Earth, far smaller than any star had any right to be. Additionally, because both 40 Eridani b and Sirius B orbit other stars, timings of their orbits allowed an estimate of their mass, and Sirius B, for example, seemed to weigh about as much as the Sun. This combination of utterly unheard of factors was initially quite baffling. For example, the famous astronomer Arthur Stanley Eddington said, "The message of the companion of Sirius when it was decoded ran, 'I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox.' What reply can one make to such a message? The reply which most of us made in 1914 was, 'Shut up, don't talk nonsense.'" And fair enough. They seem to be made of something completely outside of human experience. In order to provide a uniform unit of reference for all the objects I'm discussing, I'm going to be comparing their density to that of this cherry tomato. I wanted to use grapes, but they're not in season. If this was made out of white dwarf material, it would weigh about as much as an African elephant. What on earth can account for such an impossibly high density? The answer came less than a decade later with the development of quantum mechanics, and Ralph Fowler used the newly developed Pauli exclusion principle to come up with a solution. Now, don't worry, I'm not going to get into a whole lot of esoteric mathematics here. But the question that needs to be answered is this. With the radiation pressure turned off in the dead heart of the star, what point of stability provides the next equilibrium against the crushing force of gravity? Now, the Pauli exclusion principle basically amounts to a sort of quantum snobbery. Electrons, it turns out, don't like being the same as each other. They can't be close to each other and have the same amount of energy. So if you squash a whole bunch of them together, then for quantum reasons, some of them will have more energy than you would otherwise expect. And this energy provides a pressure that stops the further gravitational collapse of the star. For reasons I'm not going to get into, this is called electron degeneracy pressure, and the stuff inside the white dwarf is called electron degenerate matter. Now, once they've reached that equilibrium point, they are dead objects. They're not burning any more fuel, and they're not generating any more energy. But they have a large amount of residual heat left over from their last years as a star, so they are white hot. And electron degenerate matter is opaque to radiation, meaning that it takes a very long time for that heat to escape from the core of the white dwarf into space, so they stay hot for a surprisingly long period of time. The universe is 13.8 billion years old. The oldest white dwarfs have been around for an appreciable portion of that, but they're still at temperatures of thousands of degrees. It's been estimated it could take over 1 trillion years for them finally to cool all the way down to just above absolute zero and become cold cinders drifting through the void. No longer white dwarfs, now black dwarfs. Now note, that's quite different to black holes, which are completely different objects, and I'll cover that in my third video. However, not all white dwarfs will go that quietly and meekly into the night. A small proportion of them will annihilate themselves in some of the most spectacularly violent explosions seen anywhere in the universe. This happens when the white dwarf is part of a binary system with another star, and they orbit each other closely enough that the white dwarf's gravity can pull material off the surface of its companion. That material will fall onto and accrete on the surface of the white dwarf, and when it reaches a critical threshold, the fusion reaction will restart in a flash, and the white dwarf will blow itself apart in a supernova explosion that will briefly outshine its host galaxy. So that's a brief overview of white dwarfs and a glimpse into the future history of the Sun. Now, a key assumption made in this video is precisely that we're talking about stars roughly equivalent to the Sun in terms of mass. In my next video, I will cover what happens to stars that weigh significantly more than the Sun, and they become different objects called neutron stars. Thanks for watching.